10.3, multiplying radical expressions. So these first few examples, we want to go ahead and multiply the radical expressions together and then simplify as much as possible. So remember, to multiply radical expressions, there's one thing that is absolutely necessary. The root or the index must be the same. Notice this is a square root, cube root, cube root. So when they are the same, you can go ahead and combine them into one radical by multiplying the radicands together. So this one would become the square root of 4 times 10, which is the square root of 40. And we ask ourselves now, does 40 have any perfect square roots? If you can't see it right away, just simply on the side, do a little bit of scratch work and draw yourself a prime factor tree and look for the factors that you need that are repeated. In this case, since it's a square root, we're looking for pairs. So let's see, 40 is 2 times 20, 20 is 2 times 10, 10 is 2 times 5. So we're looking for a group of 2. Well, we see that the 2's are a group of 2, so we can pull out a group of 2's, and then whatever is left on the inside, you multiply those factors together. So that would give us 2 times the square root of 10. Here they're both cube roots, so we can go ahead and multiply them together. That is the cube root of 7 times 3 is 21. X times x squared is x cubed. When it comes to variables, it's pretty straightforward because this dictates everything. This tells you that you are looking for groups of 3 of the exact same factor. So if you notice here, I have x cubed, which means x times x times x. So I do have a group of 3 x's, and I can pull out an x to represent that. So this will be x times the cube root of 21. 21 is simply 3 times 7. There is no factor that appears 3 times. Okay, let's do this one. Same thing. We see we have a index of 5, index of 5. So we can multiply the insides together. So x cubed times x to the 10 is x to the 13. That's using our laws of exponent laws. And then there's no need to open this up. If you open this up, it'll take you a very, very long time to actually write this. Remember, y plus z, that entire expression raised to the power of 12 means you want to multiply this entire thing to itself 12 times. That would take way too long, so just leave it. Just leave the base as y plus z. Notice here we have a base of y plus z. So y plus z to the power of 12 multiplied by y plus z to the power of 12 is simply y plus z to the power of 24. We add the exponents together. Now same as the last one. This dictates what we are looking for. We are looking for groups of 5 of the same factor. I have 13 factors of x. How many groups of 5 can I pull out? Well, I can pull out 2 groups of x's, 2 groups of 5 of x's, okay? And I have 24 y plus z, factors of y plus z. How many groups of 5 can I pull out? I can pull out 4 groups. Y plus z to the power of 4. Now whatever's remaining we have to keep inside the radical, and this is very, 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 very important. Don't forget that. Okay, if I have 13 x's and I pulled out 2 groups of 10, that means I pulled out 10 x's, which would mean I have 3 left. So I would have x to the power of 3. And if I had 24 y plus z factors and I pulled out 4 groups of 5, that means I pulled out 20 of them. That would mean that there are 4 remaining. And that would be our final simplified expression. Okay, so now instead of multiplying, we simply have an expression that we want to simplify. We will use the same idea. So let's look at this one. Once again here, we can do some scratch work to figure out if 120 has any perfect squares. So 120, we can break that down using prime numbers. So we know 2 goes in 60 times. 60 is 2 times 30. 30 is 2 times 15. 15 is 3 times 5. we are looking for pairs, right? Because we're in a square root. So we simply have a pair of 2's that we'll be able to pull out. And then a product of these factors will remain on the inside. So 5 times 3 times 2 is 30. So we can pull out a 2. Now I have 2 factors of x. If I want a pair, I can pull out an x. And if I have 3 y's, I can pull out 1 pair. Now what I'm left with on the inside, we said was 30. I don't have any x's left on the inside, and I have 1 y left. Now, what we were talking about in the first section with the absolute values, I want you to note that in every section after 10.1, it states, assume no radicands were formed by raising negative numbers to even powers. So it's basically telling us that none of these variables represent negative values. So we don't have to worry about the absolute value bars. Okay, let's look at this one. Okay, so 16, we want the fourth root. We know that is 2. I have 18 A's. If I want groups of 4, I can pull out 4 groups of 4. B, I have 12 B's. How many groups of 4 can I pull out? I can pull out 3 groups. And if I have 21 C's, I can pull out 5 groups of C's. What do we have remaining? Remember, don't forget your index. 16 all came out. I had 18 A's. I pulled out 4 groups of 4, which is 16 of them. So I have 2 remaining. So A squared. I had 12 B's. I pulled out 3 groups of 4, which is exactly 12. So no B's remain on the inside. And 21 C's. I pulled out 5 groups of 4, which would be 20. So I would have 1 C left.